Hello. We are going to start off with the topic of wave optics now that we have finished with ray optics. Now, this wave optics, that is the study of optics as waves, the light as light waves, this was given by Christian Huygens in the 1600s after the failure of the theories like the corpuscular theory and the Newtonian concept. So they were not up to the mark in explaining all the phenomena that are associated with light, especially the likes of reflection. Well, that was explained by the corpuscular theory. However, the case of refraction was not that easy to explain. The case of interference of light and then that of diffraction, all these phenomena could not be explained properly by the corpuscular theory, which had to be dropped. And therefore, Huygens wave theory was more popular as it could explain all these phenomena. And in fact, after the case of Maxwell's electromagnetic theory, where the wave theory could well explain the case of polarization as well. So, although it wasn't explained by Huygens, but still uses the wave concept and the electric and the magnetic field that are associated with the electromagnetic waves. Nevertheless, they were helpful in explaining the case of polarization. So all of these phenomena could be explained by wave theory, and hence it was very popular up until the time came that we had to consider the particle nature of light as well, which will be dealt with in the dual nature of radiation. Now, as far as Huygens principles are concerned, we will be discussing about the Huygens principle first. But before that, before going over to the Huygens principle, what we will be considering is a term known as wave front. Now, what do you mean by a wave front? Now, it is quite a common experience that we observe ripples, circular ripples on the surface of water from a point of disturbance. So, suppose we have still water surface and we observe or we give some kind of disturbance, maybe a droplet of water on the surface, or even any kind of stone or any kind of disturbance that would disturb the membrane of water. When that comes in contact with the surface then forms these kind of ripples, which you have observed very well. So these ripples that you can see on the surface of water, they are circular ones because the disturbance is taking place on a plane. Now, what you observe, what you do not really observe is that actually these are waves which are propagating from the point of disturbance radially outward, like this. Now, so this is the point of disturbance where when a stone has been dropped or a droplet is has been pushing the membrane downward. As the membrane goes downward, the area surrounding it, given by the dotted line, that has gone up. So there will be a wave which has propagated like this, then gone down, then again gone up, and then again gone down and up like this. So there's a wave which is propagating in the outward direction, not a single wave, but multiple waves like this. The lower portion is blank, while the upper portion of the waves have been provided with the dots or the dashed lines. So like this, you have the waves traveling outward from the point of disturbance. So in each case, what you observe is that the line or the dashed lines that I have drawn, they are connecting the points which are lying on the crest of each of these waves. The waves are obviously composed of crests and troughs. If you remember from the case from the study of wave motion in the previous year. So this is a wave, and the topmost point is the crest, while the bottommost point is the trough. So all the crests over here, they have been joined by these dashed lines in each of those waves that you see, which have generated from a common source. So there is the source of disturbance from which there is a crest over there, the trough, followed by the crest, followed by the trough, and again the crest. So what you are observing is that all the crests have been connected by dotted lines. The first set of crests that you see, they are connected by the first circular dashed lines. Then the second set of crests again by dashed lines, and the third set, and so on. It will continue up until you have the space for the disturbance to propagate. Now, this is in two dimension that you are observing. In two dimension, what you are observing is that the lines are joining in a circular manner. Imagine this case happening in three dimension, where the propagation could have been in the upper region as well. Instead of being restricted to a plane, the disturbances or the waves would have propagated in all possible directions, which happens in the case of light. So when we consider light as a wave, there must be a source of disturbance from which the wave these waves propagate in all possible directions, and the crests of these waves can be connected through a circular, not a circular line now, but a circular sphere. And this is known as a wavefront. So what does a wavefront do? A wavefront connects all the, it can be imaginary or it can be visible. If you, as in case of water, you are seeing the ripples being formed. The ripples are actually those wavefronts. In case of light, however, you cannot see light itself, but from light you can view different objects. So in case of light, you have a source from which the light rays and light waves are emanated into a medium, and the wavefronts thus formed will be spherical in nature. So these wavefronts are spherical, considering the direction of propagation of the waves in all possible coordinates, that is the x, y, and z coordinates in three-dimensional space. So this is in three-dimensional space, obviously. However, you will only be able to represent those three-dimensional spheres in the form of circles in two-dimensional papers that I'm using. So we are restricted to that. Now, again, if I consider a source to be at a very large distance, then you will have a very big circle. Obviously, I'm not drawing a very big circle, but at least we can imagine this to be a very big circle, and a very small portion of this very big circle is in the form that small portion that I can consider over there, that will be a flat surface or a planar surface. So the wavefront associated with the source lying at infinity, which is at a very big distance, the wavefront will be planar wavefront. Although it is spherical, but it is planar wavefront considering the size of the sphere. Just like the case of Earth, the Earth appears to be flat uh, as we see it, but it's actually a big sphere. But we are considering a very small portion of this big sphere, and that is why it appears to be flat. So there we have a planar wavefront. And then finally, we can have for a linear source, like for a line distribution, you have the light rays to be moving in all possible directions simultaneously. So you have these circles everywhere, and these circles everywhere from that line source would form a cylindrical wavefront. So this is a cylindrical wavefront when the source is a line source. Now, what does Huygens principle tell us? Now, as far as the concept of wavefronts is concerned, what we can say is that if we have a source over here, then probably we'll have a wavefront of it. We are considering a small portion of that wavefront. Now, this is what we call as a primary wavefront. And as far as the Huygens principles are concerned, the first of the two principles that we are going to discuss now states that every point on this primary wavefront of the due to the source, each point on this primary wavefront will be a source of disturbance itself and will lead to a secondary wavefront or secondary wavelets, especially small wavefronts that are associated with those sources of disturbance. They will constitute the secondary wavelets. So these small circles are wavelets, which are nothing but small wavefronts. So these are secondary wavelets. So that's the first principle given by Huygens. So each point on a primary wavefront is a source of secondary wavelets. And because these wavelets have their sources to be oscillating with the same phase, then these wavelets uh, will be oscillating in the same phase as well. So all the exterior points, if considered and if connected tangentially by an envelope, then that envelope would represent a secondary wavefront. So due to a primary wavefront, why a secondary wavefront? Because they are always going to be in phase, because the very sources which have produced them, those points on the primary wavefront, they are in the same phase. And that is why these wavelets, which are caused due to the oscillation of their sources, which are in phase, will always be in phase with one another. And each point that I've drawn tangentially, I've connected tangentially, uh, forming the secondary wavefront, each point will be in phase. So for a primary wavefront, you are going to get a secondary wavefront. And likewise, this secondary will be a primary for another secondary wavefront. So it continues one after the another. So for a primary, you are going to have a secondary wavefront. There is a law associated with why the wavefronts cannot be constructed in the backward direction. Because again, here also I can connect this tangentially. But I'm not going to do so. Why? Because there is not going to be a secondary wavefront for a primary in the backward direction, that is towards the direction of the source. Now, why is that? Now, there's a popular theorem known as Stokes' theorem. Now, the Stokes' theorem states that the intensity of the light that we are going to get from a source, that is directly proportional to a factor 1 plus cosine of theta. Now, theta here is the angle between the light ray which are emanated from the source. Now, these are the light rays which will be emanated from the source in the outward direction. And the direction of propagation of the wavefront will always be outward as well. If that is the case, then for wavefronts propagating in the outward direction, we have this angle theta to be equal to 0. And because this angle theta is equal to 0, that means the intensity is going to be finite, because 1 plus 1 is going to give you some value 2, and that is obviously acceptable because that's a certain amount that is associated. Now, if we are going to consider the wavefront propagating in backward direction, then that would create some sort of problem, because in that case the direction between the ray and the direction of propagation of the wavefront will be given by the angle theta, which is equal to 180 degrees. As in that case you have theta to be equal to 180 degrees, you have cosine of theta to be equal to -1 in that case. So 1 minus 1 would result in 0, and there would be no intensity in the backward direction. So Stokes' theorem proves that why we do not have any wave to be propagating, or a wave front to be propagating in the backward direction. Now you must also keep in mind every time that the light rays being radially directed, that is, they are directed along the radius of a spherical path that we are considering for the wavefront, from the source being at the center. The surface of the wavefront is always perpendicular to the light ray, which means that every time you construct a wavefront and a light ray, they must be at mutually perpendicular directions, which is what we are going to use in the next cases in order to prove the laws of reflection and refraction by using the Huygens principle. So first up, we are going to verify the laws of reflection using the Huygens principle, for which I have provided you with a diagram. Now here what we see is that we have two parallel light rays, let us say they are 1 and 2, and this first ray, the ray 1, that strikes a reflecting surface at the point A. Now as it is reflected in that same medium from A right up to A dash over there at the top. Now as it goes from A to A dash, the second ray, which was in phase, and we had a wavefront AB, a planar wavefront AB. So that wavefront was the incident wavefront. So we have AB as the incident planar wavefront, obviously, because the light rays are parallel, so the source is at infinity, and that is why the wavefront has to be planar wavefront. So we have a planar wavefront AB, and while this first ray gets reflected from the point A to the point A dash, the second ray that travels from B up to B dash down there. Now in the meantime, we have both those points B dash and A dash. They will be in phase. Why? Because the points A and B were in phase, so having them getting reflected in the same medium or moving in the same medium, they would have had that many number of waves and that particular wavelength intact, and that is why they will be completely in phase. So A dash B dash here is the reflected wavefront. So this is a reflected planar wavefront. Now as we can see that those wave fronts are obviously perpendicular to the propagation of the rays. So we have two right angle triangles over here. We have a right angle triangle as ABB dash, and we have another right angle triangle A dash B dash. Now in both of those right angle triangles, what we find is that AB or AB dash is the common side in each case, which is the base. It is the base of each of those triangles. I mean the hypotenuse in this case, not the base, the hypotenuse in this case, because it's in front of the right angles. And then uh, nevertheless, that is the common side. Then we have the angles. Now the angles are right angles, so we have ABB dash, the right angle, and we have A dash B dash as the right angle, both of them being the same. And then what we know is that because the wave is getting reflected in the same medium, its velocity remains the same, its speed remains the same. So in a given time, when the second ray travels from B to B dash, the first ray has traveled from A to A dash, such that we are having the reflected wavefront over there as A dash B dash. And let us say the time is t, and the velocity of each of those waves in that medium is v. So v into t is the same for each of them. So from side angle, side axiom, these two triangles are congruent. So the triangle ABB dash and AA dash B, they AA dash B dash, they are congruent. And from congruency, what we can see is that the corresponding parts of congruent triangles are common. And therefore, what we have is that this angle I, that is the angle of incidence now, that will be equal to this angle of reflection. Let's see how. Because this is I, this angle that you see over there that I've just drawn, that is going to be 90 minus I, because that angle plus the I angle would have resulted in 90 degrees. Similarly, from that dot dash normal that I have drawn, if this is 90 minus I, from that normal, you would have had this entire angle to be 90 degrees. So this angle that you see over here, that has to be equal to I. Similarly, in the other triangle, this angle will be equal to R. So in both those triangles, as the corresponding parts of the congruent triangles are common, so you have I is equal to R. And from that, the law of reflection is proved, that the angle of incidence is equal to the angle of reflection. Now, all these rays that we have drawn on a common plane. So obviously all the rays are going to stay there. They are on the same plane. So that proves another law of reflection, which states that the angle of incidence, the angle of refraction, as well as the normal drawn at the point of incidence, they will lie on the same plane. Obviously they are lying on the same plane. We have drawn each of them on the same plane. So both the laws of reflection are verified, and that by using the case of wave fronts, as we have considered in Huygens principle. So this verifies the laws of reflection. Now we can move over to the law of refraction. So that's the image that we consider for the case of verification of the laws of refraction by using the Huygens principle, where again we have two rays which are incident on an interface which is separating two media, where in the first medium, medium 1, you have the velocity of light as v1, and in the second medium you have the velocity of light as v2. And these two light rays, they strike the interface. This is the interface that is separating the two media, and on that interface, as the first ray strikes the point A, the other ray is at the point B, and AB is the incident wave front, as we already have discussed. So AB is the incident wave front, as we have already discussed in the previous case uh, that we studied, that is right above, that is law of reflection. So this is the incident wave front, and then as the ray gets refracted onto the other medium, the first ray that is, and it moves from the point A to the point A prime over here, then in that given interval of time, the second ray that is, that travels from the point B to the point B prime. Now, as we know that the frequency remains constant in even if you change the medium, so the number of waves that would have been formed in a given interval of time as it travels from A to A prime will be the same as the number of waves that will be formed in that particular interval of time for the second ray from the point B to the point B prime. So as a result of that, what we get is they remain in the same phase, and hence we have the same wave front. We have them at the same phase at the point A prime and B prime, both those rays, and so we have A prime B prime as the refracted wave front. So A prime B prime is going to be the refracted wave front. Now, we have the angle of incidence and refraction in case of the first ray that is getting refracted. We need not be concerned about the second ray getting refracted, because that's definitely going to go into the other medium in the same direction as that of A. If I am to draw this would continue in the second medium parallel to uh, A prime. So that's not a big deal to consider. What we need to consider is the verification of the laws of refraction. Now, all of these rays, they are on the same plane, obviously. So that law is verified, which states that the incident ray, the refracted ray, and the normal that is imagined at the point of incidence, they all lie in the same plane. And they do, as we can see over here. Now, as we derived in the first case, the angle of incidence there will be equal to, in this case, within that triangle, we will also obtain an angle of incidence I. And if that is the angle of refraction R that we have over here, now that being the angle of refraction, and that being the normal, the dashed line that I've drawn. So this will be 90 minus of R, and the other angle being 90 degrees, that is the angle between the ray and the propagating ray and the wavefront. That angle is definitely going to be 90 degrees, that is the A prime angle. So the other angle is going to end up as R. So we have the angle I and the angle R in two right angle triangles. So in those two triangles, from the first top triangle, that is ABB prime, we have the sine of I to be equal to that is equal to the perpendicular over the hypotenuse, that is equal to BB prime over the hypotenuse, in this case is AB prime, and the sine of the angle of refraction on the triangle below, that is AA prime B prime, that is equal to uh, that is equal to the perpendicular again, which is equal to for the angle R, the perpendicular in this case is AA prime, over the hypotenuse is again the common side AB prime. Now from that, what we have is the ratio of the sine of the angle of incidence to the sine of the angle of refraction. That is equal to, simply the AB prime terms get cancelled out, as you can already uh, see over there. So this is a BB prime over AA prime. Now BB prime is actually the distance traveled by the ray in the first medium in a given interval of time. Let us say that is V. Let us say that is T. So this is equal to, the velocity in the first medium is V1, and the time taken supposedly is T. And in the same time, the the first ray gets refracted and moves from the point A to A prime in the second medium with a velocity v2. So from this we have those time factors cancelling out. So we have v1 over v2, which is nothing but the refractive index of the second medium with respect to the first, as we have already discussed in the case of refraction of light. So we have this ratio of the sine of the angle of incidence to the sine of the angle of refraction as the refractive index of the second medium with respect to the first, which is a constant for a given pair of media, which again verifies the other law of refraction. And thus both the laws of refraction, both the laws of reflection and refraction, uh, well, the laws of refraction in this case, both the laws, because they are lying on the same same plane, and the case of the ratios being equal to a constant, that is verified, as well as the law of reflection that was verified previously. So we have both these verifications done on the basis of Huygens principle. Therefore, wave theory is a successful tool to explain all these kind of phenomena that are taking place in optics. So we'll keep it over here, and in the next video we shall be getting into the case of interference and many more related topics to that. Till then, thank you for watching.